So we talk about microarchitecture. So overview of the microarchitecture. It is the hardware implementation of the CPU's instruction set architecture. That's the ISA, defining how instructions are executed. The data part is the core components responsible for processing data, working in tandem with the control unit to execute instructions like arithmetic operations or memory access. So we'll talk about the CPU components. The control unit acts as the CPU's conductor, decoding instructions and sending control signals to direct the data path and then other components. It ensures the data moves correctly through the CPU to execute instructions like add or load word. Types: the hardwired uses fixed logic circuits for speed, common in modern CPUs like ARM Cortex. Microprogrammed uses microcode for flexibility. So we are talking about the data path. The data path is a CPU's workstation, handling the flow and then the processing of data for each instruction. It consists of interconnected hardware components that execute arithmetic logic and then data transfer operations. Think of it as a kitchen where ingredients or data are processed into dishes. That's the results. Where under the shelves, that's the control unit. So these are the key components of the data path. So we have the components, and the components we have the registers, the arithmetic logic units, the buses, the multiplexers, the memory interfaces, the program counter, and then the instruction register. And then under each we have the description, we have the role in instruction execution, and we have the examples. So registers, general purpose registers. In RSV, there are 32 registers with X0 always holding 0. They store temporal data like variables in the program. For example, add X1, X2, X3 reads operands. From X2 and X3, writes the results to X1. Special purpose registers. Program counter holds the memory address of the next instruction, incremented by 4 in RSV or 32 instructions. Instruction register temporarily stores the fetched instruction for decoding. Memory address register holds the addresses for memory operation. Memory data register holds data being read from or written to memory. Register file, a small memory bank with 2 read ports and 1 write port. For add X1, X2, X3, the register file reads X2 and X3 in parallel and writes the results to X1. So when we are going to talk about buses. Data bus transfers data between registers, ALU, and then memory. For example, it carries the results from the ALU to the register. Address bus. Address bus carries memory addresses for instruction fetch or data access. Control bus carries control signals from the control units to direct data path operations. The multiplexers acts as switches to select between multiple data sources. For example, in ADDI X1, X2, 10, a multiplexer selects the immediate value 10 as one ALU input. For example, for add X1, X2, X3, the multiplexer selects register operands, but for ADDI, it selects an immediate value. Memory interface connects the data path to main memory for instructions like load word or store word. For example, load word X1, 0, X2, the data path sends the address in X2 to memory via the address bus, and data bus returns the load value to X1. Data path operations. The data executes instructions in a series of steps guided by the control unit. 1. The fetch. The PC sends the instruction address to memory. The instruction is loaded into the IR. The control unit decodes the IR, signaling the register file to read operands. Example x2, x3 for add, execute. The ALU processes the operands. Example adds values, memory if needed. For load or store instruction, the data path accesses memory. Write back. The result is stored in a register. Example x